There we go. All right, we continue with other questions. So now we're in chapter 6. Again, if you have any questions on anything at any point, just let me know. We can cover a lot more questions if you guys want to on a specific topic. All right, so I'm recording, that's double checked, and we can continue. Okay, so we are given a fair coin. You flip this coin twice. The two flips are independent. For each heads, you win $3. For each tails, you lose $2. Consider the random variable, the amount of money that you win. Use the definition of expected value to find this expected value. Use the linearity of expectation to find this expected value. Okay, so part A, we have to do two things. That's a good review question. So here you're forced to use the definition of expected value. So you have to know this definition. And the definition of expected value is what? So you look at the sum, and maybe I usually always write something like this. So let the big Rx denote the range of x. So you don't have to write it like this, but I like to write it like this because it kind of makes it clear. So I'm looking at the range of x, and I look at every value in the range of x. So in x, and I might as well not write it in latex. So I look at every value in the range of x, and multiply each of these values by their corresponding probabilities. So that's the definition of expected value. Okay, so we need two things. We need to understand what is the range of x and what are these probabilities. And once we have these two, we just plug them into our formula. So what is the range of x here? X is the amount of money that we can win. We flip a coin twice. So what are the different amounts of monies that we can win or lose? So the word win is, take it lightly. This is really more about the expected amount of money. It's the expected earnings. You could have a negative winning, right? So here, just be careful. So here we don't have a choice but to describe the set here. It's not all possible values from -4 to 6, right? So what could happen? Well, I have two flips, so it means that I really have 4 different outcomes. Either I have heads, head tails, or tails tails. So if I have head tails, what do I get? How many monies do I win? Well, I get 6, right? Now you don't need to write this in order. So this is the biggest amount, but it doesn't matter. So it's a set, so order doesn't matter. So here, next thing that can happen, I flip a head and a tail. So I win 3, but I lose 2. So I get $1. And then the next thing that can happen is what? I lose $2 twice. So I lose -$4. So here we only care about the values of this function. Okay, the next thing that we look at is the probabilities that each of these values is achieved. And these probabilities are not too hard to compute. Well, actually, they should be pretty easy to compute. What is the probability that x is equal to 6? Well, that's the probability of getting head-head, which is just 1/4. What about the probability of getting 1? X is equal to 1. Well, that's the probability of what? If I got 1, it means that I either flipped head tails or tails head. That's equal to 2 over 4. Next, the probability that x is equal to -2 is equal to 1 over 4. It's the probability of tails. Okay, now we have our probabilities, we have the range, so now we just write this summation. Here there's only 3 values, so we can expand it easily, right? So I look at -4, and I multiply it by the probability that it's equal to -4, which we just, sorry, it's not -2, it's -4. Yeah, exactly, thank you. So it's -4 times the probability that x is equal to -4, which is 1 over 4. Plus next value, 1 times the probability that x is equal to 1, which is 2 over 4, plus 6 times 1 over 4. And now you just compute this. So it's 1 over 4 plus 6 over 4, which is 7 over 4. No, sorry, I brain farted. Went way too fast here. This is -1. So this is -3 over 4, right? I think. 4 over 4. Eesh. Yes, thank you. So 4 over 4, which is equal to. So math is hard. So this is -1 plus 2. So that's 1. Okay, then what is it telling us here? Here it tells us to use the linearity of expectation to find the expected value. So what is the idea here? You're forced to use linearity. So how can we use linearity here? What would you guys do? If I tell you use linearity of expectation to compute this thing, this expected value, how would you use it? So what is this telling you to do? There's not too many things that you can think of. So think about this one for like 30 seconds. Yeah, so if I'm going to use linearity of expectation, it essentially means that I need more than one random variable. I need some more random variables. So the idea is to look at different random variables. What random variables could I be looking at for this problem? I want to compute this amount of money, the expected money that I win. Yeah, that is perfectly valid. So here, one thing that we could do is we could look at define 2 other random variables, right? We could say let y be equal to the number heads, and w is equal to the number of tails. So what do we know? What is the relation of x between x, y, and w? Well, the relation is that x is equal to what? Is equal to 3 times the number of heads that I get minus 2 times the number of tails. And what does that mean? It means that this expected value here is equal to the expected value of 3 times y minus 2 times t. Now you use linearity. Linearity tells you that this is equal to 3 times the expected value of y minus 2 times the expected value of tails. Now you observe. What is the expected value of tails? Is this easy to compute? So yeah, it should be a half, right? Or is it a half? Or something different than a half? Is it 1? So here, let's be careful, okay? Here, the expected value of tail is what? How many tails could I have? Either 0, 1, or 2. So the expected value of tails is 0 times the probability that I get no tails. 0 tails plus 1 times the probability that 1 tail plus 2 times the probability that 2 tails. Now, so this goes away. Probability of getting 1 tail is a half. Right, so this is a half. Probability of getting 2 tails is a fourth times 2. That's a half. This is 1. Easy to make a mistake here. Now, the thing that you also observe is that the expected number of tail is equal to the expected number of heads. The coin is fair. Coin is fair. So here I can just say that, okay, well, actually, this is equal to what? This is equal to 3 times the expected number of tails minus 2 times the expected number of tails, which is just the expected number of tails, which is 1. Right? Because these two things are the same, I have 3 times the same thing minus 2 times the same thing. I'm left with 1 time one of this. Is this the only possible answer? No. You could have looked at different variables, right? You could have defined some indicator variables if you wanted to, and kind of have the same idea. That would be one way to make use of linearity. Yeah, no, it's much simpler than that. So, and that's kind of a good trick to keep in mind if you're looking at money earnings, in which you have several scenarios. You're counting the number of times something happened, and for each time this thing happened, you get some fixed amount of money. Well, you can break it. You can break the amount of money you win in terms of the number of each scenarios that happen times their corresponding earnings. And that's what we did here. We had one scenario, so number of heads times the earning per head, plus the number of tails times the earning for tails, right? I think that's pretty much it. Is that okay? Is there any question for this first part here? No questions? Okay, so we continue. So part B. You flip this coin 99 times. These flips are mutually independent. For each head, you win $3, whereas for each tails, you lose $2. Consider the random variables, the amount of money that you win. Find the number, the expected value of E of Y. So here, what would we do here?
I think you just make a mistake for variables here, where you were saying let y to be the number of heads and like w to be the number of tails. So x will be 3y minus 2w.
Yes, so thank you. Yes, absolutely. Thank you. Yep, you're absolutely correct. So here you don't need a binomial. You could use a binomial, but try to make use of part A. And yeah, the idea is, so there's several things that you can do here, but here the idea is to look at each individual tosses. So there's several things that you can do, and again, I'll mention one thing. So one possible thing is to be, okay, so maybe I could, well, y is used here, so maybe I could switch the y and switch it to the v instead. Right? So just to avoid confusion. So now y, what am I going to do? The amount of money that I win. Well, the amount of money that I win is equal to the amount of money that I won or lost on each toss. So what I'll do is now, here the trick is to define some, it's almost like an indicator variables. So let yi be the amount of money won on toss I. And I do that for all i's between, so personally I don't like the letter I, so I write k. So I'll just write k. So for all k between 1 and 99, I look at the amount of money that I won on toss k of toss. So now the idea is that, okay, well, what is true about y and these, what is the relation between y and these random variable? Well, the amount of money that I win in total is certainly equal to the sum of the monies that I win on each roll. And so it's the sum of these YKs. And now, is this not, oh yes, I'm making several typos today. Thank you. Again, another typo. So now, what is the idea? The idea is now, okay, well, again, I can use linearity of expectation. I want to compute this thing. So I'm going to compute this thing. And now by linearity of expectation, this is equal to the sum of these expected values. It should be okay. Now, the point is, do we know these expected values? What is the expected value of yk? We just found it, right? It's the expected amount of money that you win on first on a And, oh, wait, I need to be careful. It's not exactly the same. Here we were flipping 2 coins. Now we're flipping 1 coin. So it's not exactly the same. So here, what is the expected amount of money that I win on 1 toss? So this expected amount of money, what is it? Well, I have 2 different values. It's either I won 3 or I lost 2. So it's -2 times the probability that yk is equal to 2, and -2, sorry, plus 3 times the probability that yk is equal to 3. This is equal to -2. What is the probability that I lose 2? If it's I get tails, right? Yeah. So it's half plus 3 times a half. What is that? That's 0.5, exactly. So that's a half. Oops. Like that. Now you just plug this back in your summation, right? Plus expected value of y is equal to the sum of this thing, the half, which is just 99 over 2. And yes, so for the person that said it's binomial, you're absolutely correct. You could just say it looks like a binomial, but so if you wanted to make use of the binomial, you'd have to kind of go back to what we did here. So how could you make use of the binomial? If you don't like to define these indicator variables, you can still make use of the binomial as follows. So how would I say that I'm making use of the binomial? So how would I do that? So what I would say is something like this. So let again, I would have to define 2 other variables. Let v be the number of heads and w be the number of tails. I is equal to 3 times v minus 2t. Now the expected value of v, that's a binomial distribution. Correct? The expected value of v, the expected number of heads in 99 trials, independent trials, is a binomial distribution. So here you could say, note that v follows, has a binomial, or is a binomial random variable, with probability of success. So here, the important thing is, if you want to use a geometric or binomial distribution, just specify what your notion of success is. Here, the notion of success is being ahead, having head or getting head is equal to a half. And now you can say we know class. We know from class that expected, or you could, maybe it's even better to just say the expected value of v is equal to 99 over 2 from theorem seen in class. Right? So you multiply the number of trials by the probability of success. And now you note also that, well, E of t is equal to E of W is equal to E of V. And did I make the same mistake above? I think I did. Yes, I did. So this should be a W. And this should be a V. There we go. Right, so if you want to make use of the binomial random variable that you know, and that's one way to do this. Right? But however, y does not really follow a binomial distribution. It kind of does, but have to be a bit careful. Is there anything wrong with just saying using x and saying that if y is equal to so I'm not sure what Stephen, what you're saying. So what is x here? Did I define x somewhere? What is your x? I see. From part one, right? But the part one is a bit, that's the thing, is you can't really use part one. Part one was not about one flip, it was about two flips. Oh, I see. No. Oh, okay. I see what you're saying. So it's not, it wouldn't be x that we would be looking at, but x is the amount of money that I win over two flips. It's not over one flip. So I cannot really use x here. That's if that's what you're saying, we have to be a bit careful. Do you see the difference? This is two flips, not one flip. Yeah, so you could almost do that, yeah, and it pretty much comes down to just understanding that. Yeah, you could do that, but I think sure, why not? Yeah, I think you could do that. You could divide. Oh, I see what you mean. Yeah, you could. I have two flips. If I want one flip, I could divide it by two, and I think it's a fair approach. Right. So I think you could also do, well, here we found the expected value of monies that I win for two flips. If I want for one flip, I can take this expected value that I found, this one, and divide it by two. So the expected earning for one roll is half, and then you multiply it by the amount of rolls. You could also do that. That is a fair thing to do. So it's just from the definition. Right? The expected value of the winning on one toss, what is it? I just use the definition of expected value. I have two options. Either I lost -2, I lost 2, or I gained 3. Are we good for this one, or is there any other questions? So I think there's several ways to tackle this question. I think someone asked, how do you know if it's a binomial or distribution or geometric. Just to review and say it once, a binomial counts the number of successes in n identical and independent trials. So the word identical is important. If your trials change from one to another, then it's not a binomial distribution. The things that I do, the things that I'm doing needs to be independent and repeated. So the word repeated means it's the same trial that I'm making over and over. So it counts the number of times I succeeded, and that's your part as a student to say what is the notion of success. If you want to say a random variable has a binomial distribution, then you have to say, okay, what is the notion of success? If you do that, that's good enough. And what is the probability of success? A geometric distribution repeats trials until the first success. So binomial counts the number of successes in some fixed amount of trials, whereas a geometric distribution repeats trials until the first success. All right, next question. Did we do this one? I don't think so, but this is starting to be a bit repetitive. I don't think we did this one, right? So assume we flip a fair coin twice independently of each other. Consider the following random variables: the number of heads, number of tails, and the number of heads times the number of tails. We want to find the expected value of these three random variables. And then we want to establish whether or not they are independent. Okay. So it's worth going over because, again, and I think I made an announcement this morning, when you're asked to show independence of random variables, don't, well, at least I'm not sure if you will get full marks for just an English argument. You should resort to the definition. So here we'll have to use the definition to show whether or not these random variables are independent. So what do I mean is, some people sometimes, in some of your assignments, I read sometimes, well, oh, well, z is a function of x and y. So it does depend on x and y. Therefore, these two variables are not independent. And that's kind of not formal enough. And is it always true? They just try to avoid such answers. Just stick to definitions. So first of all, before I'm getting ahead of myself, we need to find the expected values of these three random variables. So we know the definition of expected value. We've kind of already dealt with these expected values. So we flip a coin twice. What is the expected number of heads? Well, we kind of found it already, right? This is just the previous question. So here, I'll be a bit lazy. So the expected value of x is equal to the expected value of y, which is equal to 1. And that's from question 6.5. Right? So this is just this part. Okay, now what is the expected value of z? This is the only new thing. So here, if you just wondering, so quick questions. Are people being kicked from the meeting or losing connection? No? Okay, good. Just let me know if there's some connection issues, because some of you are like leaving and coming back, which is fine. It's just sometimes I'm just hoping it's not on my end. No, that's fine. I'm making sure that there's no connection issue or whatever. It's all right. Well, sorry about that. All right, so here I think there was one question. So here, yes. So what Ian said, just be careful. The only thing that's coming over from 6.5 is this line here, these two lines. Remember that W is the number of tails. So when I say the expected number of tails in two flips, that's the same, right? These two lines are exactly the same. The rest is discarded. It's these two lines that I'm looking at that are the same. Does that make sense? I think it's Ian, right? Ian or I. Yeah, okay. Okay. So now we have to find the expected value of Z. I think there was another question. The other question is, in case it's actually independent, do we have to show it for all values? And the answer is yes. Yes, that is the answer, which is why you should not have too many equalities to check on your exam. If you have a random variable, two random variables, and now you can think of, oh, well, for example, if X had 4 different values and Y had 4 different values, that would be way too long to check in an exam. It would be 16 different equalities, and in my opinion, that's too much. So this works well in multiple choice exams, right? But now this is a written exam, so I'm not sure how much you can depend on this trick. But yes, if you want to show independence of random variables, that's the thing that you have to do. You have to go through these equalities. If you want to disprove independence of random variables, you disprove one of these equalities. So regardless, if you're asked to prove or disprove independence, you should at least write the definition. If you don't write the definition of independent random variables, it's fine, but it's not really fine, to be honest. Like for marking purposes, stick to the definition for this type of question. So anyways, again, I'm getting ahead of myself here. We're just dealing with the expected value. So the expected value of Z is equal to the expected value of X times Y. Okay, so now important, and I think that's why I took this question. Can I write this? Can I write this thing here? Is this thing equal to this? No. And why are you guys saying no? Maybe it is true. But what does this depend? Exactly. So you're right. I cannot write this. Maybe I could write this. But this depends, or this relies on showing that X and Y are independent, which we haven't done. So I cannot use this. Maybe it is true. I don't think in this case they are. Yeah, that's the thing. Nothing is preventing you to do part 2 first. You could do that. So just be careful. If you want to use this line here, you would have to show that X and Y are independent. So here we'll just stick to the definition. So here, what is the range of Z? What are the possible values that Z can take? So remember, X is the number of heads and Y is the number of tails. One and two, that's correct, but are these the only two values? There's 0, that is correct. And you're still missing 1. What is the other value you're missing? 4, exactly. So here Z is not related to really these two flips. It's just, that's the definition of Z. So I look at every values of X, every value of Y, and I look at every different product. So the 4, you might think, well, does it make sense? It doesn't have to. It's just a function. So here, what are the possible values? It's because X could be 2 and Y could be 2. Now, think about what I said. They cannot be 2 at the same time, but in terms of function, X is a value, 2 is a value for X, and Y is a value for, 2 is a value for Y. So I could have 2 times 2 here. So here, close, it's 0, 1. If both are 1, we have 1. Right? If X is equal to 1 and Y is equal to 1, we have the value 1, 2, and 4. So here, really, how did we get the range of Z? We just looked at the possible products of these two guys. You don't think about, oh, well, if X is 2, then Y has to be 0. You don't think about it this way. You look at every possible pairs of values of your two functions. You multiply them by each other. So there's a pair 2, 2. So that makes the value 4. Now, what is the expected value or the probability that Z is equal to 0? Well, do we really need to find it? We don't care about it, right? Because when I'll compute the expected value, I'll do 0 times the probability that Z is equal to 0. So I don't really care about that probability. So it's not really needed. So I'll just start as the probability that Z is equal to 1. What is that probability? So if Z is equal to 1, what do I know?
Means that the head and tail are both. Sorry,
Yeah.
like the first.
Yeah.
Sorry.
No, that's, I understood what you meant. I think we all did. Yeah, it means that X is equal to 1 and Y is equal to 1. Okay. So now what do we do? What is this thing?
A half.
Why is it a half? So this comes from question 6.5. So just be careful. What might confuse you is that this X is not the same as section 6.5. Not section, but number 6.5. And this Y is not the same as question 6.5. But we have computed the expected number of heads in 2 flips. We have done that in question 6.5. Okay, so someone said a half. Why is it a half?
Because I have, for 2 flips, there are 4 possibilities. So for all those 4 possibilities, I can get 2 options that I can have 1 head and 1 tail.
That's perfect. Yeah, that's exactly what you should be saying. So in short, what you can just write is the probability of head tails or tails head. These are the 2 other only options, right? And that's 2 over 4, which is a half. So that's perfect. Okay, what is the probability that Z is equal to 2? You do pretty much the same thing. So if Z is equal to 2, what needed to happen? So think in terms of the values. So if Z is equal to 2, Exactly. So I have two cases, right? So x is equal to 2 and y is equal to 1 is one case. Or x is equal to 1 and y is equal to 2. Now we think. What is that probability? 0, exactly. This is not possible, and this is not possible. Right? I cannot have 2 heads and 1 tails because I'm flipping the coin twice. So this is equal to 0 plus 0. There are only 2 flips. Next, probability of z is equal to 4, the same idea. So here, this probability is x is equal to 2 and y is equal to 2. Is this possible? No. Same reason. Exactly. So actually, this expected value of z is pretty simple, right? It's 0 times the probability that, so maybe I'll just still compute. So because it might be useful later there, so I'll just mention the probability that z is equal to 0. Maybe I can conclude it from there. Yeah, so I'll check the probability that z is equal to 0, but in theory, for the expected value, well, this is 0, this is 0, so I'm only left with a half times the probability that z is equal to 1. So z is equal to a half. So again, I'll just write this. So the expected value of z is equal to 0 times the probability that z is equal to 0 plus 0, or I should say 1 times 0 plus 2 times 0. No, it's not 1 times 0, it's 1 times a half, sorry. Plus 4 times 0. That's just a half. Now, note, what is the probability of z is equal to 0? Yeah, I'm finishing this part and then we'll, thank you. I'm finishing this part and then we'll take another break. So here, last question before the break, and then we'll continue. What is this probability? It should be pretty easy to answer. Yeah. So it's just a half. Now note, once you have these 3 probabilities, well, they should add up to 1. So here you can immediately find that it's a half, but if you don't like this, you can just say, well, it's x is equal to 0 or y is equal to 0. Which is equal to the probability that x is equal to 0 plus, or in here I can actually say this is just, I'll shortcut. So here there's an or, right? So you might be tempted to use inclusion exclusion, But here I won't use inclusion exclusion. I won't mention that this intersection is empty. I'll just list the two flips that produce x is equal to 0 or y is equal to 0. It's head, head, or tails, tails. And that's equal to half. So the fact is that this OR is disjoint. And that's more clear in this OR. So you don't really need to say it here. You can just follow with these two outcomes. Okay, so we'll take a break now. So
is it
yeah.
and or like the last one? Is it probability that x is equals to 0 or y, or probability that x is equals to 0 and?
It's or here. Is that what you're asking?
Yeah, but why?
So it's z is equal to 0. So z is the product of x and y. So z is equal to 0 if this guy is equal to 0 or this guy is equal to 0. Correct?
If we and, like, it will be the same reason, right? Will it be a difference? Because the rest of them we used and.
Yes, but here, well, here, carefully, right? We used or here. But here, the reality is that if I want to write, these are two different cases, right? It doesn't matter what the value of y is if x is equal to 0. The product will be 0. So if I write the and here, well, that's not possible. So that would be 0, right? If x is equal to 0 and y is equal to 0, that would be 0. I cannot have 0 heads and 0 tails. So the wording is important. Right? If I tell you the product of two things is equal to 0, it means that one of them has to be 0. And that's exactly what I'm saying here. So the wording is important. So okay, break time will continue around 2:50. So yeah, 2:15 is a good break time. So I need to stop the recording.